Hello everyone, I am Dr. Inderjit Singh from Department of Mechanical Engineering in City University Ludhiana, and today we are going to discuss the topic, one of the prominent topic from strength of materials, that is bending stress in beams. So we are going to start with an introduction. So beams are the horizontal members, they are and they are generally taking the transverse type of loads and they are subjected to bending load. So why we are studying the bending load? Because we have to find the maximum value of bending stress, and along with that we have to find where is the location of the maximum bending stress. So for this we have a procedure, we have a derivation, and we have a bending moment equation. So today we are going to discuss each and everything regarding this topic. So the beams, they are the horizontal members, so and they are subjected to transverse load. So as you can see in the figure, the beams are initially straight, and when they are subjected to transverse loading, so they transverse means when they are perpendicular to the axis, the cross section of the beam. So when they are subjected to such type of load, they are subjected to bending load. We call it as transverse loading. So the beam will try to bend, it will try like you can see in the figure, the beam will have a tendency to bend in this curvature, right? The beam is initially straight, and due to the externally applied load, that is transverse load, the beam will try to deflect the shape like this as shown in the figure, right? And such type of stress which is induced in the material due to this type of load, that is known as bending stress. So once again let's look in the figure. So initially the beam is straight, supported on a two members, and with the help of arrows you can see the transverse load that is applied on the beam, and the beam will have the curvature like this after bending, right? So the beams are subjected to transverse loading. We are studying beams. In case of columns, they are subjected to axial type of load. In case of beams, they are subjected to transverse type of loads. Axial will it will apply in like in the direction of the axis. The axis of the structural member will be like this, and the axial load will act like this, right? And in case of beams, we have a beam that, and the load will be in the transverse direction. So that is known as transverse loading. So and due to that, as a result of the transverse loading, bending moment is produced in the beam. So we will study these few parameters on which the bending moment and the bending stress depends. Before starting with the procedure, we have some assumptions. We have a theory known as simple bending theory, or it is named as theory of simple bending. So before starting that theory, let us discuss some assumptions that are taken into consideration before finding the equation, before deriving the equation that is used for calculating this type of stresses. So the first and foremost assumption is the beam is isotropic and homogeneous. So I hope you have already heard about this term, isotropic and homogeneous. That means throughout the material, entire length, entire section of the beam, so it will have consistent properties throughout the material. The material properties will be consistent throughout the material. That means the density properties, all the properties, they will be consistent throughout the material. The second one is the beam is initially straight. The beam it will be initially straight. There might be some manufacturing defects. There might be some deflections initially due to manufacturing, due to installation, due to assembly. But we are considering that the beam is initially straight. For our analysis purpose, we are assuming that beam is initially straight, and the cross section is constant. You know, due to manufacturing or somehow there might be some changes in the cross section. It might not be same throughout. It's not possible to make consistent cross section. Let's say there might be 2%, 5% changes in the cross section in the area, but for the analysis purpose we are assuming that the section of beam, that is having constant cross sectional area. So we are assuming that the cross sectional area is consistent throughout the length, and initially it is unstressed, so there is no initial stress in the material in the section of the beam. The elastic limit is not exceeded during the loading time, so we are staying within the elastic limits. The Young's modulus of material, that is same in tension and compression. So in the upcoming few minutes you will see that there is two type of stresses in the beam. So when it is subjected to the loading, there might be tensile stress. In some layers we will have tensile type of stress, we also have compression type of stress. So we are assuming that the Young's modulus of the material, that is same in tension and compression. And the next one is the plane cross sections. We are assuming that the cross sections are plane like this, and even after the bending, the plane cross sections, they will remain plane like this. There might be bending, but the cross sections will remain plane. They are not going to skew like this. And the radius of curvature is large as compared to the dimensions of the beam. So what is radius of curvature? So the beam will bend like this, and there will be a radius. Okay, if you complete the radius of from the arc, the beam will bend like an arc, and if you complete the radius, so you will have a radius of curvature. Okay, the beam is going to have very small deflection in radius. So if you complete the arc from the beam, from the deflection, the radius will be very large as compared to the dimensions of the beam. So that are our assumptions before starting the theory of simple bending. So the theory of pure bending, or you can say the theory of simple bending, it says that the beam, when it is subjected to transverse load, so we are assuming that there is zero shear stress. So we are assuming that there is no shear stress in the material. Okay, and with the help of that we are defining and we are calculating the different parameters on which the bending stress will depend. So that is known as pure bending or simple bending. That means there is only bending type of effect, there is no other effect than bending, there is no shear effect in the beam. Okay, and the stresses that are going to set up in the material due to this pure bending, that is known as simple bending stress. Simple bending and the corresponding stress, that is known as simple bending stress. Okay, and in the figure also you can see we have two type of loads, axial load and transverse load. In this case, in our case, we are going to have the transverse load. Okay, and again the stress is due to the transverse type of loading. Right. So in the next few minutes we are going to discuss the procedure, how mathematically we are calculating what is the effect of different parameters. We are going to have geometrical parameters, material properties, the conditions. So according to that, how the bending stress will vary. We are going to find the location of stress. What is the location of maximum stress? So with the help of the topic that we are going to discuss, we can find the stress at any location, and accordingly we can redesign the component for the bending conditions, right. So that is with the help of theory of simple bending. So what we are going to do, we are taking a very small element, as you can see in the figure below. We are taking a simple element and we are taking a very small size, very small section of the element. Okay, and we are going to analyze this small section before and after bending, and we are going to apply some mathematical relations, and we will apply some simple strength of material relations like stress and strain on different layers. With the help of that, there are two major concepts used in that will be used in the upcoming few minutes. The first is the simple stress and simple strain that we are going to apply on different layers. Secondly, we are going to apply very basic mathematics like finding the length of arc or some relations like this. Right, so we are considering a beam that is subjected to simple bending, and we are considering a very small section dx. We are naming it as dx, that is a small part of this beam. And there are two transverse sections, like in this transverse direction we are we are considering two elements. The first one is AB, we are naming it as AB, and second is CD. So we are going to analyze these two sections before and after the bending. Initially they are parallel to each other, so you can see with the help of two colored lines, one is blue and other is red colored line. Initially they are parallel to each other, AB and CD, and after bending, so they are after bending you can see they are now deflected, and AB and CD are they are now changed to A dash B dash and C dash D dash, right? And if you consider the section, the complete section A, B, C, D, initially it was a rectangular section, now it has been deflected to A dash, B dash, C dash and D dash. We are using a dash to rename the shape after the bending process. And you can see the layers, the length of the beam. If you consider any layer, you can see the length of the layer, it is not same before and after. So that is what we are going to study. What is the change in the length of the layer, and that we will apply on different layers, right? And if you consider this red colored line, that is AC, the line AC, or you can say the layer, the topmost layer AC. Okay, now you can see that it has been shortened, the length has been reduced to A dash, C dash, right? So and you know from the basics, if the length is getting reduced, that is a compressive type of stress. Okay, so we can say that this layer, the top layer, the layer AC, that is subjected to compressive stress, right? And if you carefully see this blue colored line, the green colored line, that is BD, right? It is getting elongated, it is getting increased to B dash, C, D dash, right? And if something is going to increase in the length due to any type of load, we name it as tensile type of stress. Okay, so we can say that the bottommost layer, the layer BD, that is subjected to tensile type of stress, because the length of that layer is getting increased. Okay, and in between you can see from the top the length is getting reduced, and when we are moving towards the bottom, the length is getting increased, right? From decreasing to the increasing, if we move from top to bottom, right? And if you carefully see, in between there might be some layer that is not getting elongated and neither getting reduced. Okay, so here the concept of neutral axis comes into effect. Okay, so in the beam you have seen that the topmost layer, that is under compression, and the bottommost layer, that is under tension. Okay, and in between we have a layer that is having no effect. That means there is neither elongation, neither reduction in the length. So that axis, that layer, we call it as neutral axis. Okay, and we are going to name this with the help of the symbol N, or it's called as NA for the neutral axis, or NN. So before and after, the length of this neutral axis will remain same. And this is the very important concept to note for the upcoming equation, because we are going to use the length of this layer in the upcoming slides, right? And this layer is termed as neutral axis or neutral layer also. Okay, so by definition, this theory of simple bending, it is saying that the stress in the material, in case of a beam, the stress will vary as we are moving away from the neutral axis. It directly depends upon how much away we are from the neutral axis. It depends upon the distance from the neutral axis. Okay, I am repeating this again. If we are close to neutral axis, the effect is very small, or on the neutral axis the effect is 0. And if we are moving away from the neutral axis, that is we are moving at a distance from the neutral axis, the effect becomes large. Okay, so the increase or decrease in length, okay, that directly depends upon the distance from the neutral axis. Okay, if we are going to the top, the topmost layer, we will have the decrease in length, and if we are moving very like at the last layer, bottommost layer, there will be increase in length. So that means it directly depends upon the distance from the neutral axis. So from the next few minutes, we are going to derive the expression for the bending stress, and in this expression we are going to have lot of parameters on which the bending stress will depend. Okay. So bending stress in the material, it depends upon lot of conditions. It depends upon the working conditions, loading conditions, we can say how much load is applied. It depends upon the geometry. What is the geometry of your beam? What is the moment of inertia? What is, and then it depends upon the material, which material we are going to take. So all these properties or parameters, they will be considered in one single expression, and it will help to find out the maximum bending stress, and also along with that it will help to find the stress at different locations. We are not only dealing with the maximum bending stress, but also we are going to find what is the location height wise, the layer wise, and also with like the length wise also, what is the location of maximum bending stress, right? So once again we are going to consider the same element again, the small element dx with the length dx. Okay, and again we have named them A, B, C, D. Okay, they are normal to the axis of beam. We have the axis like this, and they will be normal to the axis of beam. Okay, so you can see in the figure before and after, the layer AC, now it has been changed to A dash C dash, and similarly the layer BD, that has been changed to B dash D dash. Okay, now if you carefully notice, we have to carefully see this thing, that we are going to apply very basic mathematics in this case, okay, to find out the length of the layer, and we are going to compare the length with the original length. Okay, this is how we will find the strain in the material. Okay, if you remember the principles of SOM, so we need to calculate stress and strain, and if you know what is the change in length, we can find the strain in the material, right? So we are going to compare the two lengths before and after, and with the help of that we are going to find the strain in the material, right? So the first step is the strain variation. So before and after, you can see in the figures, we are considering a layer EF, right? That is at a distance of y from the neutral axis. We are having a layer EF at a distance of y from the neutral axis, and after bending it will deform to E dash F dash. Okay, it will be shown with the help of a red color line, right? So you can see before the line is initially very straight, and after bending it becomes like an arc. And you know how to calculate the length of an arc? We can find the length of arc by finding the angle and by having the radius of curvature. Okay. So what is strain? Strain is your change in length divided by original length. That is the ratio of change divided by the original length. Okay. So we are going to find the change in length. So mathematically we can write it as E dash F dash, that is your final dimension, minus initial dimension. Initially it is EF, right? So the change in length is E dash F dash minus EF divided by the original length EF, right? Now here the mathematics comes. We need to find the length of EF, and if you carefully see, the length of EF, that is the same as the length of neutral axis NN, right? And n is also equal to n dash, that is the length of neutral axis. It will remain same before and after. And from the second figure, figure number B, we can find that this length, the length of n dash, right? We can find the length of arc n dash, and that will be equal to r into theta, that is radius of curvature for the arc into the angle subtended by that arc, right? So we can find the length of arc, it will be equal to r theta. okay. And similarly we can find the length of arc E dash F dash. So now the radius is r plus y, because it is at the distance of y from the neutral axis, so the radius becomes r plus y multiplied by the angle, that is theta. So E dash F dash will be equal to r plus y into theta, okay. So we are going to substitute these values in our formula. So after summation we will have this relation, that is r plus y theta minus r theta divided by r theta again. So if you simplify this relation, so everything will get cancelled out except these two parameters. So we will have y divided by r. Theta can be taken out and cancelled, and r is also cancelled out, so we are left with y upon r. So that is our first relation, that is strain in any layer. So what is this equation denoting? That the strain in any layer that can be calculated, it directly depends upon the distance of that layer, that is y divided by radius of curvature, okay. It is directly proportional to the distance from the neutral axis, okay. The second step is calculation of stress. So stress is, you know, we from the strain we are going to calculate what is stress in any layer, okay. So from the Young's modulus, from this theory we know that stress upon strain is equal to Young's modulus capital E. So we know the material will have some value of E, constant property, and we have calculated the value of strain earlier. Just we have calculated the value of strain. So if we submit these values, so E will be equal to sigma divided by strain, that is y upon r, okay. So if we rearrange this equation, the stress in this layer, that is equal to E multiplied by y upon r, okay. And you know, the material property, that is the Young's modulus, that is also constant for any given material. The radius of curvature, that is also constant throughout, okay. So these two are constants, and we are left only with the y, the parameter y, that is the distance of layer from the neutral axis. So once again, this layer, the stress in this layer, that directly depends upon the distance from the neutral axis, okay. So we can rewrite this equation. So sigma upon y, after rewriting we have sigma upon y, that is equal to E upon r, right. So with the help of this equation we can find the we have the relation between stress, between the location of layer, and between the material, and between the radius of curvature. So we have material property, geometrical property, we have the condition, okay. So these parameters are involved in the first part. So this is the first part of the equation, sigma upon y is equal to E upon r. So now you can see the figure, we have a neutral axis, and again we are summing it up, and the maximum, the location of maximum bending stress. So that is either at the topmost layer, either at the bottommost layer, okay. So the maximum is on the outermost layer, we say it as outermost layer, it can be on the top, it can be on the bottom, and the zero stress is in the neutral axis, okay. And if we talk about lengthwise, okay, there are different type of beams. We can have simply supported beam, we can have cantilever beam. The lengthwise, the location of that point, it depends upon the type of beam. So in case of simply supported beam, it can be near to the center. In case of cantilever beam, it is near to the fixed end of the cantilever beam. So like as shown in the figure. So the next concept for the second part of derivation, that is moment of resistance. So the moment of resistance, it is basically internal resistance offered to the external applied load. Resistance in any case, it is internally offered by the material to the externally applied load, right. So in this case, the moment of resistance, it is the resistance offered to the externally applied moments, okay. So different layers, all the layers, we have seen that all the layers are under some kind of stress, okay, and that means that there is some kind of force that is acting on these all these layers, okay. and the force will have moment about the neutral axis. You know, we are having some distance and we are having some force, so force will result in some kind of moment. So moment is force into distance, so we are having some force at some distance acting at some distance. Due to that we will have the moment created by these externally forces. Okay, so that is known as the moment. The total moment of all these forces, all the layers, they will have forces having some distance and they will act as a moment. So all the moments, the combine, if we combine all the moments, we call it as the total moment of all the forces, or in short terms we call it as moment of resistance. Okay, and for the equilibrium, the moment of resistance, that is internal, that is equal to the external applied moment, bending moment, that we call it as bending moment. So mathematically we are finding the expression. Okay, so first we will calculate the force on any layer. We are talking about any layer having a distance y. So but how we can find the force? Again, the stress is force upon area. From this value we can calculate the force in any layer. Okay, so the force will be equal to stress multiplied by area. Okay, so and we are talking about the very small area, so we call it as the small area is known as dA and multiplied by the stress. Okay, and from the previously derived expression we know that stress is equal to stress upon y is equal to E upon R, and from this relation we will use the parameters E upon R into y in place of stress. We are substituted this value and multiplied by the area. Okay, this is just for one single layer, and if we talk, if we calculate the moment, this is the force only, this we have calculated, this is the force, and moment will be force into distance. So distance will be y. Okay, so moment is force into distance, and multiplied by the distance of this force we will find the moment of the given force. Okay, so this whole parameter, this whole equation multiplied by the distance y, this will be the moment of resistance for one single layer, right. So we are having E upon R into y square multiplied by dA. Okay, and this is just for one layer. If we calculate for all the layers, we have to do integration. Okay, that will give you m, capital M, that is integration of all these forces, right. And you know the moment these two parameters, that is E, that is Young's modulus, and R, radius of curvature, they two are constant values, so they are taken out of the integration and we are left with integration of y square into dA, and y square dA is you know nothing but moment of inertia, or you can say second moment, so that is equal to the moment of inertia. Okay, so from this relation we can write y square dA equal to I, and we have the relation m, that is E upon R into I, and rearranging this equation, so we have m upon I is equal to E upon R. Okay, so from here we the previously derived relation, that is sigma upon y was equal to E upon R. Now in this relation it is m upon I equal to E upon R. Okay, so from all these two combinations we can write that m upon I is equal to sigma upon y, and that is equal to E upon R, right. And this equation, that is a very famous equation, it is known as bending moment equation, right. Let us rewrite this equation again. M upon I sigma upon y is equal to E upon R. So bending moment equation, so parameter wise the first is moment of resistance, along with that we have the units Newton millimeter or Newton meter. Second is your moment of inertia. For the section, it depends upon the section, the cross section. If you are using rectangular beam, if you are using circular beam, it can be I section, T section. So the moment of inertia will be it's a geometrical property, right. It it will be based upon the dimensions you have selected for the beam. So the bending stress sigma Newton per millimeter square, this is what we have to find. Y is next, the parameter y, it is the distance of layer from the neutral axis, how much away we are from the neutral axis. Okay, The E is Young's modulus. This is your material property. So this equation helps you to compare different materials. If we select steel, if we select aluminium, if we select wooden material, different type of materials, what will be the changes in the stress? So the units you already know, it will be Newton per millimeter square. And the last parameter R, that is your radius of curvature. What is the radius of beam that is bent into an arc? So again the units will be millimeter. Okay, that is all for this topic. This is the bending moment equation, and it's very important in finding out the location of the maximum bending stress in case of bending type of load. Thank you.